Welcome. I'd like to tell you about displacement current. This is the addition that James Clerk Maxwell made to Ampere's law. So here are the laws that we've been studying in AP Physics. And you notice that this is Gauss's law for electric fields. This is Gauss's law for magnetic fields. This is Faraday's law. And this is Ampere's law. And by the time we get done with this video, we're going to add one more term to Ampere's law, and that is called displacement current. So see how we still have Gauss's law for electricity, or for electric fields and for magnetic fields, Faraday's law, and then this is Ampere's law now with one addition. This addition right here, that's called displacement current. Okay, so and that was added by Maxwell. So let me explain. Remember, if we have a wire with Maxwell's or with Ampere's law, if you want to know the field, say right here, let's see, the direction of that field would be, if you use your right hand rule, it's out toward us. But to get the actual strength of this field right here, we put in an Amperian loop. I want that to be a circle with a radius r, and then you can think of this. This is actually a circle in 3 dimensions, so it's kind of going this way. And we thought of this as a membrane. That membrane that was stretched across the circle, and so we said that the current through mu naught times the current through the Amperian loop is equal to the closed loop integral of B dot dl. And so for this case, how much current is going through the Amperian loop? Well, all of it. So I'll just say mu naught times I, all of it is going through. And then on this side, if we look, the B's are going tangential to the circle. That's the direction B's are going. And so are the DLs. So the B and the DL are in the same direction, and so we can get rid of this dot product because they're in the same direction. And so then the next thing I can do is I can pull the B out of the integral, because for every point on the Amperian loop, the B is the same. These B's are the B's on the Amperian loop. And so for every point on the Amperian loop, the B is the same value. Why would we expect it to be stronger here than here than here? And so if you pull that out and you add up all the DLs, well, let me do that the next step. So if you pull that out and now you sum up all the DLs, they will just add up to 2 pi r. So B is equal to mu naught I over 2 pi r. Okay, so that's Ampere's law. Okay, but here's the thing, is what if you had a situation like this, where there was a capacitor, and it was charging up, so the current was flowing through here. Now, current doesn't flow through a capacitor. The charges go onto the capacitor, but they don't go through the capacitor, because this is an insulator, whether it's air or a dielectric of some sort, wax or paper or something, but it doesn't flow through. But look, if there is, when the current is flowing, there is a magnetic field here, and if I put my Amperian loop there, you know, we might be able to calculate it. But what if I had the membrane, instead of having the membrane go like this, what if I had the membrane go like this? What if I distorted it a little bit and had it go through the capacitor? Oops. Okay, well then we would agree there's a field there, but there's no current going through this membrane. This is the membrane, and there's no current going through there. I'm not using this as the membrane. I'm using the cup shape as a membrane, and there's no current going through there according to Ampere's law. And so what Maxwell did then is he said, well, maybe if we had one more term, you could account for that. And so this is what he did. He said that the current through here, normally you would say it's mu naught times I, but that would be equal to mu naught. This is the left side of Ampere's law. Mu naught times I is the left side of Ampere's law. So mu naught times I, but I is dq dt. And so, yeah, so the current here, dq dt, is related to how much charge is the capacitor is gaining over time. In fact, the dq dt, the gain in charge of the capacitor over time, is equal to the current right here. So, so that's what we're going to say. We're going to say that mu naught times the change in charge on the capacitor over time is also current. And so what we're going to do with that then, again going with the left side of Ampere's law, I threw this mu naught in here because that's on the left side of Ampere's law. So mu naught times the derivative with respect to time, and now I'm going to put a q in there. Now that q, let's figure out what that q is. For right now, I'll just make it a q again. But inside of a capacitor, the electric field inside of a capacitor is equal to sigma over epsilon naught. We derived that in our unit on Gauss's law. So where sigma is the charge per area, so that's the charge per area of one of the plates over epsilon naught. So that's the electric field inside of a capacitor. The electric field would look like this. And it might fringe out a little bit on these sides. Okay, so what I'm going to do is I'm going to solve this equation for a q and put it into there. So let's see, if I bring the epsilon naught on the other side times E times A, that's equal to q. And so I'm going to now put that into there. So that's going to be equal to mu naught times the derivative with respect to time of q, but for q I'm going to put in all this stuff. Epsilon naught E times A. Okay, so turns out that the epsilon naught is constant. It's just a constant, so it's going to be mu naught times epsilon naught. I pulled that out of the derivative, rather. And then it's the derivative of E times A with respect to time. But E times A is the electric flux. And so that is going to be our new displacement current. That is also going to be equal to the integral of B dot dl. Now, I'm not suggesting that that when you want to know the magnetic field out here, you have to add these two. It almost seems like I'm suggesting that with this equation. With this equation, you have to add this plus this. You either do one or the other. So if you're going to use this as your membrane, then you would only have this term. But if you were going to use this as your membrane, then you would use this term. Okay, so this is called displacement current. This whole term right here is called displacement current. And so what it's saying is the rate at which the flux in here changes with time times a constant. So the rate at which the flux changes with time times a constant, epsilon naught times mu naught, that is equal to, that's equivalent to a current. Okay, why that's nice is because now we have a lot more symmetry with these two laws. Just look how symmetric these are. E, B, magnetic flux, electric flux. And that's displacement current. That's going to be the beginnings of our understanding of electromagnetic waves and how they can how an electric field will make a magnetic field and vice versa. And so it's going to give us a good explanation of how electromagnetic waves can travel through space. All right. Thank you. Bye.